Here we go. Hello, everybody. Are we here? Let's see. Hello, everybody. I just checked to make sure everything's working on YouTube. See if I turned up. Yes, I'm there. So hopefully everything's all right. On previous occasions. Yeah. Right. I think it's working on YouTube. So on previous times I've had problems with StreamYard with various things, and I've got two computers on the go this time, so if one starts playing me up, I can try running over to the backup. So down to business. If I add to screen, I'll be got it in the wrong place. One of the problems with StreamYard is that I can mess up your slides. So I've just gone through my slides and hopefully they're all right. It's a lot of slides. We get there in the end. There we go. So you've had a preview of what's coming up. So the topic of today's talk is Atomism. I've found out I might be mispronouncing it. There's several ways of pronouncing Atomism. So forgive me that. So before going on to my talk, which is here, I would do the fundraiser. We need more money to keep going. Please give us some money.
Hello, everyone. I'm David D. Hilster, president of the John Chappell Natural Philosophy Society. During the past 2 years, we have used annual fundraising drives in order to keep our organization's presence alive and well on the internet. Both years we have been successful in that the monies collected have been enough to keep us afloat. This year is our third annual online fundraiser, and once again we are counting on your support. But first, I want to thank everyone who pays their annual memberships through our automatic online system. Your support is vital and provides us with important funds to keep the CMPS afloat. Hopefully, as we continue to grow, we will be gaining more and more automatic memberships so that these fundraising events won't be necessary. But we are not quite there yet. This year, we will be implementing several changes to our online system. Several to save money and lower our annual expenses, and another to better our discussion platform. First, we will be moving our websites and databases to another server that has graciously volunteered to host us at a much reduced rate. It currently costs us $1,400 a year for our dedicated server, given that we need complete control over our own software. The new server will give us and allow us that control, but only for $250 a year. Second, we will be moving away from BuddyPress, which is a Facebook-like plugin for WordPress, to using Discourse. BuddyPress was an interesting experiment, but the upkeep of the plugin and its general design don't really fit what we need. What we need is a robust and well-accepted discussion forum, and that is why we'll be moving our online discussions to Discourse. It costs $20 a month, which is half the price of BuddyPress. I think those currently active in our online discussions will find this new platform much more enjoyable and functional. Third, we are moving to a free version of Overleaf, which eliminates a $33 monthly fee. Overleaf was useful for us when we were publishing our own proceedings for conferences, but that is no longer needed. Our goal this year is $2,000, and I hope we can reach that goal. Whatever amount you can donate, it is greatly appreciated and needed. Your membership and donations are vital to keeping our online community of critical thinkers alive and well. To donate, go to fund.naturalphilosophy.org. That is fund, F-U-N-D, .naturalphilosophy.org. Thank you, and keep up the amazing work that is driving science forward.
Oh, hello again. I'm back. I'm unmuted, so hopefully you can hear me now. So, down to business. Today's talk is about automatism, and it's a very big subject, really. So it's only going to be a brief look at it. And automatism is really the philosophy upon which modern physics is based. So since we're a group called the Natural Philosophy Society, ideally we should be talking about it, but I don't think we have been talking about it much. So let's get into an introduction on the subject. Right. So as I said, modern physics is based upon automatism. As I pointed out, there's various ways of talking about automatism, but educators don't go into details about that when teaching physics students. Physics students don't talk much about automatism. It's one of the main areas of physics that has missed out of informing physics students. Automatism is the idea that everything, physical reality straight universe, is made from particles. And the idea seems to go back to Moses from the Bible. And in the picture there, I've got Charlton Heston, who did his portrayal of Moses in one of the Cecil B. DeMille films. So Moses was a prince of Egypt, and he was schooled in the ways of ancient Egyptian science, stroke magic. In ancient Egyptian science, from a modern perspective, it would probably disparage, and at the time they would think what you were talking about is magic. And so some think he was an Egyptian sorcerer. So he performed miracles, parting the Red Sea, etc., supposedly with the help of God. So was it by God? Or was it sort of like using an ancient science? And the idea is picked up in fiction with films like Indiana Jones and The Raiders of the Lost Ark. So the Ark was a magical device, or was it a magical device? Was it a device based on atomic physics? Because atomic physics is supposed to be coming from Moses. So you can get information about this from such sites as this one, which talks about is Moses the person who started automatism, and automatism leads to atomic physics. So the site says this. It talks about this person, Marcus of Sidon, who was a sort of Phoenician, and he was 13th century BC. And sometimes people identify that person as being Moses. And Marcus, or however way you pronounce it, was talking about automatism. So Marcus was identified with Moses, which makes it over 3,000 years ago, but it all becomes arguable. Some people dismiss the idea that Marcus was Moses, and the records are not really that clear, so people start dismissing the records about it. And so the date that automatism is really supposed to start is later with the ancient Greek philosophers. But sort of like it's in the more esoteric traditions, those ancient Greeks were going from information from ancient Egypt. So this is the two Greek philosophers from which automatism is supposed to start. So the idea of automatism has been around for over 2,000 years and has undergone a lot of development. And so going into detail about that development has, of course, been ignored from what being taught to physics students. And I suppose there would be a distant point of view that considered automatism as wrong. But modern physics, via atomic physics, etc., is based on the idea of automatism. And this is the main book I'll be referring to about automatism. It's called An Essay on Automatism from Democritus to 1960. So it's an old book now. It doesn't deal with development of automatism from 1960 onwards, but it deals with the main bits where Einstein turned up. So this is the person who wrote the book. It's Sir Lancelot Lord White. He's a philosopher and so forth. And I might be saying it. And so now what I would like about White is he was working on Einstein's unified field theory. He was around the same time as Einstein, met Einstein, etc. Unlike Einstein, White cites his information sources, and Einstein's unified field theory is based on this idea of automatism and other ideas, of course. All of this is, of course, ignored, omitted from being taught to physics students, as I keep saying. Ideally, as a physics student, should be told before being taught Einstein's relativity that the prehistory before Einstein's relativity, i.e. the starting information you need to know, is relativity is based upon automatism. So this is what White says. The conception of automatism has been the spearhead of the advance of science. Atomic ideas have led to the highest adaptive precision which the human brain has yet achieved. The history of automatism should therefore be of interest to all concerned with the human mind. Whatever the limitations and dangers of automatism, its achievements are unique and worthy of study. So White carried on and says, until a few years ago, I imagined that courses in physics included the outline of the history of automatism. And unfortunately, that's not so. Many universities, teachers and students consider they have no time for that. And my note is that White was writing in 1961 and things don't seem to have changed since then. Based upon my experience, physics students are not taught about many important things in physics that are dealt with in the earlier 19th century. So this sort of thing would have been dealt with in 19th century physics courses, but in the 20th century physics courses, they just omit it. So White carries on and he points out there's been only three basically distinct and widely successful conceptions, that's of automatism. They present striking contrast. So the first version of automatism is the Democritan Newtonian hard atoms. Really, I think you should use the word particles now instead of atoms, because atoms is now taken to mean the smallest particle of a chemical element, and really we want to be talking about the smallest particles that there are, because there's lots of hierarchy of particles. So anyway, carrying on, Newton, following the Greek automatists, adopted as most appropriate the view that the ultimate constituents of matter are themselves minute, hard, permanent, individual bits of matter of definite size and shapes. They occupy parts of space and move through the empty spaces between them. Occupied and empty space are sharply distinguished. Many scientists still think like this. Mind you, he's talking in 1961. So that's what he thought in 1961. And there's two other versions of atomism. Version B is the Boscovian point centers, and it's Boskowitz in 1758 proposed a substitute having several advantages. The smallest units are not extended pieces of matter, but persisting physical points evidence as centers of interaction. Only the spatial relations of these physical points enter physics, and every pair of such points are in interaction. And then there's the third version, which is labeled as C. It's the de Broglie-Schrödinger wave particle, and that's more modern physics. Suddenly you have this wave particle duality. So carrying on. So the first version from Newton is familiar but mathematically awkward, involving discontinuity at the surface of the atoms or particles. It is also inescapably associated with the idea that matter cannot act where it is not. Even Newton believed that all genuine physical action was by material contact, though he saw no way of using this to account for his law of gravitation. Well, the second version, version B, is ideal for many purposes and mathematically convenient. It implies that each point, atom or particle pervades space, acting everywhere except where it is itself. A valuable emphasis is thus placed on interactions or changes of relative velocity. Note the word relative velocity. What we're now talking about is going on to the idea of relativity. You're talking about relative velocity. But this idea has proved too restricted, at least as Boskowitz presented it. And I disagree with that last bit. I think it can extend to this, including this idea of wave particle duality. Well, version C is the most successful so far, but it lacks both visual immediacy and mathematical simplicity. Moreover, recent mathematical modifications have made its physical basis obscure. This has led to many different interpretations being offered of varying degrees of orthodoxy. So this is this version C, which is really the third version, is the wave particle duality one. So White carries on and he says, to these three primary ideas must be added various special conceptions of less value, vortex rings and other rotating units, twists and rotationality, elastic jelly, dislocations or holes in close packing of spheres, negative atoms of various kind, and so on. And there is also Eddington's ghost particle, from which he excluded all vestiges of materiality, so that it becomes merely a carrier of variance. So you've got a bit more than just those three main ones. So White then goes on to give more details about option C, which is the third option, which he refers to as wave particles. And that idea of wave particles sometimes gets shortened to saying wavicles. He refers to it as a disruption of the classical particle idea by the quantum particle idea. White carries on, he says, however, this disruption of the classical particle is not solely the responsibility of recent quantum theory and experiment. Remind you, he's talking in 1961 for this. For a difficulty has arisen earlier in relativity theory, so we're now bringing in Einstein. Einstein's aim was a comprehensive relativistic theory, and he knew that classical particles were alien bodies which should be represented, if possible, as unique regions in a relativistic energy field. But it was unlikely that such virtual particles or field foci could be permanent. Indeed, it seems that at any time after, say, 1910 or 1915, when it became clear that negatively and positively charged particles had definite radii associated with them, Einstein might have predicted this existence of unstable particles. So this is the thinking process that goes into it. First idea is number one, the laws express in terms of intervals the properties of relativistic space-time fields. Second, experiments have shown that some electrical particles have an effective finite radius. Third idea, therefore, some electrical particles must have an effectively finite lifetime. Or in dimensional terms, he gives you this expression relating a length with a time. And so he says, behind this line of reasoning lies the assumption that particles are quasi-localized, semi-permanent forms of relativistic field energy. They radiate lives and masses, being properties of temporary energy distribution, which for undiscovered reasons are centered at points and which appear therefore as unstable particles. There is much evidence for this basically anti-automatist view, in which there are no truly discrete entities, but only a continuum of transformations. The power of the energy concept of relativistic methods and the discovery of many unstable particles all speak in its favor. So you're seeing how it's all tying into Einstein's relativity. You start with this basic idea of particles, and then it gets extended to this, you have to consider relativity. So White points out the stags. You got for continuity, velocity of light, and for discreteness, you got things like electron charge and Planck's constant. So you've got continuous versus discreteness. So White refers to this as classical automatism, as certain encountered insuperable difficulties and radical modifications have already been necessary. And so that was the problem with the switch from classical physics to quantum physics in the early 20th century. So White carries on and says, most philosophers and scientists have agreed that to account for what is observed, it is necessary to infer entities which are not observed. An unseen universe is necessary to explain the seen. The flux is seen, but to account for its structure, we infer particles of various kinds to serve as the vertices of the changing patterns of light and shade, and so forth. So automatism is the idea below what we can observe. There are these very small particles. And so the consideration about particles, it leads to, as White points out, the following ideas. You have to consider things like space, metrical geometry, coordinates, time, reversibility, irreversibility, inertia, mass, force, energy, entropy, and so forth. So White's carried on, he says, we shall begin with broad perspectives. Physical automatism can be said to have started with Epicurus and Democritus, and after many transformations to have reached a crisis, as it seems to us now, after 1930. That's the quantum physics revolution. This span of 2,400 years, that's from when the ancient Greek philosophers are talking about it, may be viewed as the life history of an idea which is born, matures, achieves its task, perhaps, and marries another idea and leaves its progeny to carry on. The analogy has some value. So this is the life history of the idea of automatism. About 450 BC, the idea is conceived. First of all, it's welcomed, and then it sleeps between 280 BC and 1400 AD. And then in 1400 AD onwards, more rigorous play takes place with the idea. And I think that's when you're talking about the Renaissance. We're talking about here the Western Europe, where the idea of automatism for 1,000 years was mostly ignored until the Renaissance. 1600 to 1800, it is put to work quantitatively. 1800 to 1900, the chemical atom is established, and the chemical atom is the smallest particle of a chemical element, and it's not really the original idea of the smallest particle. The atom is really supposed to mean the smallest particle. And then 1900 to 1930, it's realized the chemical atom is misnamed. And then it carries on until you have the quantum revolution. So here's the geography of where automatism was taking place. It starts off in Greece in about 400 BC, moves to Italy for a bit with the Romans. They just honoured the Greek idea. Don't know how much they did for the idea. India had picked up the idea a bit, respective ideas. And then in the Mediterranean, after the decline of Rome, about 600 AD, Arab and Jewish thinkers maintained the memory of the Greek ideas and adopted some variants. And then in 1400 AD, Italy was a revival of speculative interest, and so forth. So these are the main people on automatism. You've got Newton, you've got Boskowitz, you've got Dalton, and Prout, and de Broglie, and Schrödinger. So the conclusions so far, it's basically it's a complicated issue of automatism and how it evolved to what is now in the mainstream physics in the early 20th century with the quantum revolution, and it's part of relativity in quantum physics, and it's ignored from being taught to physics students. So it's no wonder modern physics is messed up. People are not taught the basics, and the basics is this idea of automatism, how it evolved. Next, I want to pick up on Boskowitzian automatism. So, as White points out, Boskowitzian point centers, when Boskowitz was 1758, proposed a substitute. That's a substitute for the hard particles of Newton. And the smallest units are not extended pieces of matter, but persisting physical points, evidence as centers of interaction. Only the spatial relations of these physical points enter physics, and every pair of such points are in interaction. And as he points out, it's a mathematical convenience to do it that way. Then White does mention that this, he says this, Boskowitz blended atomic and quantitative methods in a mathematical scheme for unified theory of physical point centers. So what he's talking about is a unified theory, and that's coming from Boskowitz. And White does not say that of any other of the automaton theories. And of course, the development of that unified theory can get complicated. So, as far as I'm concerned, unified theory of physics starts in 1758 with Boskowitz. And so Boskowitz had these sort of influences on him. He's got Leibniz, who's had his influence on him, and it's this Italian philosopher Vico, who sort of like had similar ideas. So Leibniz, he got his monads, and so it doesn't just spring from nowhere. And so White is pointing out Boskowicz's theory is mathematical automatism, and as earlier pointed out, was a unified theory. So it's a unified theory of mathematical automatism. And the side note I want to put on that is, if you look at Pythagoras, the Pythagorean belief was about the universe being mathematical. So he's providing a unified theory in the way that Pythagoras wanted. So I put papers onto the internet dealing with things in more detail. It's one of my friends was Augustus Prince, who sadly passed away, and he's gone into a lot of detail of the mathematics behind Boskowicz's theory at such places as this. And another friend of mine, it's Professor Dragoslav, has done a talk explaining how Boskowicz's theory led to modern quantum physics or quantum theory. And White does carry on and explain how Boskowicz is connected to relativity theory. So he says Boskowicz is 1758 and Mach 1883 had stressed the relational character of all spatial observations and the consequent relativity of inertia and mechanical properties, but continuity and contact action implied for the classical mind a physical medium throughout space in a particular condition at each point, and its medium fixed the absolute space. Fixed in that absolute space was not given up easily. In 1899, Poincare asserted that absolute motion is in principle indetectable, and in 1904 he formulated his relativity principle. And the relativity principle, which Poincare does in 1904, seems to be the same sort of thing that Einstein is dealing with. So you see where this is all leading from Boskowicz. Relativity theory has its roots with Boskowicz's theory, and unfortunately Einstein doesn't cite his sources or where his information is coming from, so he doesn't mention Boskowicz, but in his talks some of the things he talks about are the sort of things that Boskowicz would be talking about. So White carried on and says, this radical transformation of physical ideas rested on two primary conceptions: the relational character of space and the universal invariance of C, the velocity of light. The continuity of the physical medium filling space was replaced by the continuity of the changing spatial relations of material entities expressed in the relativistic geometry, first Euclidean and later in the general theory of what Einstein has been non-Euclidean. So it's all a sort of development stage, and it's just unfortunate that Einstein didn't give the history of how his theory was developed from earlier ideas. So the conclusions are, so from my point of view, both mainstream and dissidents don't want to address the issue of where Einstein's relativity comes from, namely from this idea of ancient automatism, and just want to ignore it. That's why they're both in a mess. Thus, it's, as per this quote, attributed to various people. Those who do not learn from history are doomed to repeat it. And those dealing with physics definitely want to ignore their history. They want to know how physics theorizing has got to its stage from the past 2,000 years, and don't want to fill in the full details of it or teach it to physics students. So thank you. That's the end of the little talk. Let's open it up to discussions. Anybody there want to put their hand up? No. Maybe everybody's asleep. Good enough. Don't see any hands. No. Okay. Let's see what the comments say. Yeah. All right, so this person says Newton didn't know about electricity. If he did, he would have made the connection between it and gravity. Probably, yeah. Okay. So there doesn't seem to be much in the way of the comments. No. Okay. So maybe you're not following it. So hopefully my sound is all right. So okay, good. Harry is doing something there. Hold on. So nobody wants to say anything. Good enough. So if I got enough time, I can show a video. Was that? Oh, Harry is waving a hand. Move that. Okay. Hello, Harry. Your hand is going too.
Can you hear me?
Too fast.
Yeah. Am I on?
Yeah.
Okay, a couple of questions here. I have. What happened to that book about that translation of Boscovic?
Which one?
Well, you did a translation of Boscovic. What happened to that? Is that? I wrote a preface to it. Whatever.
Yeah. Well, it's just gone out there. I didn't get much. I got a bit echo. Here as well. So.
Yeah, I know.
I'll go to my other vid. I'll go to my other one.
Alexa, mute TV. Alexa, turn off TV.
Hi. Hello. Can you hear me?
I hear you. Are you talking to me?
Yeah.
Okay. All right.
I think the echo's gone. Is it?
Oh, the echo is gone. All right. That's good. regarding the question about Newton and gravity, actually, Kepler had proposed that that gravity was caused by magnetism, and Newton did some experiments on magnetism and found out that the law wasn't an inverse square law for magnetism when he did experiments with magnets. And so based on that, I think he decided that he couldn't justify gravity being a magnetic force. And that's why we have gravity as a different concept from magnetism.
Yeah.
Now, this is, I did a series of articles about this at the General Science Journal, and if people are interested about the relation between atomism and magnetism, I discuss this in detail. And one of the problems with the atomism theories that were proposed by Democritus and Leucippus was that they couldn't, that theory couldn't be used to explain magnetism. Okay, and they realized, this is mentioned by, anyway, so that's one of the reasons why atomism fell into disfavor, because it couldn't be used very well to explain how electricity and magnetism worked. Okay, and that's one of the real problems. Although Lucretius in the Roman era that you did not mention had tried to explain magnetism by a particle theory, but that wasn't particularly well received. And a large part of the reason is because they could never really figure out how they could explain the actions of electricity and magnetism by a particle theory.
Yeah. But this is a vast subject, really. And I was pointing out the development. It's I still got the echo. I think. The development of the idea of Atomism led to this wave particle duality thing with quantum physics. So it's still development.
Well, the wave particle theory presents the problem that they can't really say whether a particle is a wave or a particle or not. And so they've created a problem with this wave particle duality, and that's caused a lot of confusion. And, I noticed that in the presentation last week, Hans talked about light as a photon. He didn't even mention the idea that light is a wave. Physicists don't even think about light as being a wave anymore. And, that's kind of limiting in my view. How do you explain the wave properties of light? Well, they just think of light as being photons. So this whole wave particle problem doesn't really present much of a solution, in my opinion.
Just a minute. I see if I can stop the echo.
Okay, well, I think the echo is inherent in StreamYard, and I think that's an issue with the StreamYard. I noticed that last week when Hans was talking, there was no echo. However, Ian couldn't hear him because of the echo. So we could hear Hans talking very well, but Ian couldn't hear Hans talking because there was echoes. And I think there's an issue with StreamYard that needs to be resolved.
Is the echo gone?
Is the echo gone?
No.
I said, I think there's an issue with StreamYard that needs to be resolved. So you're not hearing me.
I'm hearing you, yeah.
I'm hearing you, yeah.
I'm just getting
Well,
an
you're
echo.
getting
Getting an echo.
Yeah, you're getting an echo. This happened last week with Ian. So apparently there's some issue about echoes and StreamYard. I'll repeat it again. It looked to me like last week when Hans was talking, we could hear Hans very well, but Ian couldn't hear him. I don't know if you recall that. Ian had problems hearing what Hans was talking about. And that's because of this echo problem that exists in StreamYard. And we haven't been able to figure out what causes it.
I don't know.
I don't know.
Do you hear an echo?
Do you hear an echo?
No, there's no echo here. I have no problem. I hear you just fine.
I've got an echo.
I've got an echo.
I know. That's the point I'm making, which is that sometimes I can't hear the other person. If I'm the host, I have a problem. I can't hear the person who's talking.
Yeah.
But when I'm talking and somebody else is the host, then there's a problem. And I think that's a StreamYard issue. Anyway, that's my opinion. I'll get off of here and let you continue on.
Yeah.
Thank you. Thank you.
With what you were saying,
though,
wave particle
duality,
and people
sort of come up with different ideas for that.
So it's still an
So it's still an ongoing issue.
The way I think
White
was talking
about is the
wave
particle idea,
which gets
shortened to wavical.
Yeah.
I'm not really sure what it means.
Wavical.
The idea is that, well, you can do a model describing reality as a wave, and in certain situations, and then you can do another model that requires that you view light as a particle, and you can do the same thing with electrons. You can view electrons as a wave in certain experiments, and then you can view electrons as particles in other different experiments.
Yeah.
That's kind of my understanding of it, but there doesn't seem to be, because of that, you can't really say that there is what the physical reality of an electron is, or light. It can be either a particle or a wave, and you can't really say what it is exactly physically. So it depends on what the experiment is that's being used.
Yeah, based on
observation.
That's not really very satisfactory physics, though. So that's where we stand.
I don't
think physics
has to be satisfactory. But that's the.
Well, they don't think so either.
Yeah.
Yeah.
So you got the mathematics, the
mathematical models,
and it
agrees with the experiment.
So they're happy with that. Yeah, and so
you want to
get a more philosophical
description
that tend to be
interesting because people come up with lots of different ones.
Well, this problem isn't really limited to relativity or quantum physics. It's in a lot of different places in physics.
Mm-hmm.
Different models are needed to explain different phenomenon, and it's not really clear how you can make a unified theory. I think a unified theory, it's never really defined you never said what a unified field theory means. And I always thought that unification meant that you had two different realms of physics, like, for instance, electricity and magnetism were viewed as two separate things. And then that was unified by Maxwell. So that was a theory of unification, electricity unified with magnetism. But I don't really see what unified field theory means in the way you're talking about it. What does it mean? Does it mean particles unified with fields? I don't know.
Well, it's going by what Einstein did. His idea with special relativity went to general relativity, and the third step would have been unified field theory, where he was trying to combine gravity with electromagnetism. And there's quite a few by him.
So unified field theory means unifying electricity and gravity.
Electricity, magnetism, in the context of Einstein is dealing with it, but modern physics is sort of talking about four fundamental forces. Einstein was only talking about two, electromagnetism and gravity. Combining two.
Well, I think standard physics today, they have something called the Standard Model, which is a supposed theory of unification, but it's based on particles, the particle concept of reality. And so you have a standard theory, and that standard theory explains all these different types of particles and their interactions. And electromagnetism now is no longer a field, it's a particle that is supposed a photon particle, whatever that means, is being exchanged, and that causes the electromagnetic force. That's an idea I can't really quite understand, but anyway, that seems to be what they're talking about. So, yeah, they have a unified standard model of physics, but it's really a particle physics model. It's not really a field theory as far as I could see. I don't see how it unifies fields and particles.
Well, when they talk about it's bosons and fermions and things, and so Higgs came up with his particle. That particle is supposed to Higgs particle is associated with the field. You got lots of things like that going on. You get in the particles associated with the field, and it's still ongoing. Because they have things like unified theory. Combines three of the forces, but doesn't include gravity. And then you have superstring theory. Tries to bring in extra based on that. So still ongoing.
Well, as far as I understand it, gravity is not unified in any way with quantum mechanics. So, I mean, general relativity. So general relativity is not unified with quantum theory, and that's the big problem that they have today. So you don't have a unification of relativity and quantum physics. Quantum physics is a particle theory, tries to explain things by particles and a wave duality. I'm not sure what that means. And but they haven't been able to unify relativity with quantum theory. It seems to me the big problem. So they're always trying to create a unified theory of something. And when you say unified field theory, do you mean electromagnetism unified with gravity? Is that what is meant by unified field theory?
That's what they were working with. For unified field theory about Lancelot White working on that.
Okay, so that's still the problem. Quantum theory and relativity. If relativity is the basis of gravity, you can't really. The two don't work together. So this unified field theory means an attempt to take two things that are that are disparate concepts in physics and put them together, and they haven't come up with a solution yet. That's my understanding of it.
But they haven't got an agreed solution.
Excuse me?
Because they got things like quantum gravity and gravity and things.
Yeah, those theories don't work because they can't get gravity, which is a relativistic space-time theory, which deals with a continuous theory of space and time. That doesn't combine with quantum mechanics. The basic ideas underlying those two different theories don't fit together at all. That's what the problem is.
Well, they fit parts of it together. My focus has been on relativity, and I think the principle of relativity has understood and things like that.
The what? What about? I didn't hear that. The principle of relativity. What?
The principle of relativity.
What about it? You said you were talking when you were talking about it. You were talking about Poincaré. Okay.
Yeah.
And it turns out that if you look at this, the French, of course, say Poincaré invented relativity because of his invention of the principle of relativity. And of course, when you read physics books, they don't tell you that. That creates a lot of confusion because they say Einstein came up with this principle of relativity. And one of the problems is that it looks like Einstein's idea about the principle of relativity is not really the same as Poincaré's principle of relativity. And then Einstein kind of later adopted Poincaré's version of it. But most people don't talk about that nor know that happened. And so everybody points to the 1905 paper and say, this is the principle of relativity in Einstein's 1905 paper. But then the principle of relativity is different in his 1916 general relativity paper. It's not the same as what he said in 1905. And so it's kind of confusing by what do you mean by principle of relativity? That has a lot of different meanings. So that's an issue right there.
Yeah, that's an issue. Different meanings. So the adoption of the relativity principle has not been that good. People have had different ideas about it.
Right, and I had a discussion with Richard Kaufman, and he asked me to comment on a paper, and he wrote down Einstein's two postulates. Okay, and I said, what's your reference for these two postulates? And he said, well, everybody knows what the postulates are. It's in all the textbooks. And I said, okay, show me some textbooks where these postulates are cited that you're referring to. So he sent me these references from these textbooks, and every one of the textbooks had a different wording of the postulates. Every textbook had a different set of words. They didn't all say the same thing, and you could interpret them differently. I'm talking about both the relativity postulate and the speed of light postulate. So nobody has ever, and I keep asking this, where is the universal everybody agrees to principle of relativity? Different books give different versions of it. What is the everybody agrees to a principle of light velocity being constant? What does that mean? All the books say something different. Where is the one authoritative book?
They haven't agreed yet.
Okay, that's something else. That's kind of maybe an off-topic issue, but I tend to agree that with respect to atomism, there's because they don't teach the history of physics. I don't know that I think there are history of science courses that you can take, but I'm not really sure they're in the physics department, or I think they're in a completely different department, maybe in the philosophy department, and probably not in the history department. I don't know enough about how universities deal with that. But they don't teach you a history of physics class as a physics major. I don't think there's a requirement that you learn the history of physics. Maybe they say, well, you should take a history of science course, which might be in the history department.
They don't teach physics students normally.
Well, then you have philosophy of science, and I think that's in a different department also as well. So I don't think physics students or science people are required to take philosophy of science classes. I was an electrical engineer. They didn't make me take any such courses. It was all, here's the mathematics of how you do these calculations as an engineer. And, and I remember taking physics classes and, it was all just, these are all the equations that you need to use. Didn't really explain where the equations came from or anything about that. Just here's the equations. And that's what they teach.
Yeah.
So how do you...
Engineers aren't taught too deeply into physics. If you want to go deep, do a physics degree.
Well, I as an electrical engineer, had to take classes in field theory, and I believe personally that those field theory classes that were taught by the engineering department of engineering, electrical engineering department, were much more detailed than anything that a physics student was required to do in the physics curriculum. And I never met any physics students in any of my electrical engineering classes. Now, I did meet a physics student when I was in graduate school, and he came to me and he said, I don't understand how to solve these equations. Well, I understand that you as an electrical engineer were taught how to solve these differential equations in your field classes. I thought that was really interesting.
Yeah, that's mathematics.
Essentially, this physics student was saying, if he was a graduate student in physics, was saying that electrical engineers had a better grasp on how to solve differential equations in physics than physics majors did.
Yeah, but as an engineer, you don't go into the theory of mathematics. There's philosophy of mathematics.
That's a whole other completely different topic, the philosophy of mathematics. That's a whole other thing. Even mathematicians aren't taught that. They're just taught, here's algebra. Here's a bunch of theorems. They're not taught, philosophy of mathematics, which is another subject. I guess you'd have to take a class in philosophy of mathematics. I think they exist.
They do.
But I'm not sure that you as a mathematics major are required to take such a course.
You wouldn't, no. If you're just doing pure mathematics, you wouldn't probably do the philosophy of mathematics.
So, anyway, I guess we're getting a little far afield from this.
Yeah.
I commend you for trying to, I commend you for taking this as an issue of talking about atomism, which is indeed a fundamental precept of modern physics, which isn't really, basically well, how should I put this? It's not taught in school. Maybe if you're interested in that sort of thing, you can take that as an elective by going to a history of science class. But I don't know that all universities have such history of science classes. I really it depends on, maybe if you were to go to, I know that possibly maybe Harvard, because there were history. There are people who famous philosopher, history writers on history, and I can't really think of their names now. There was a guy that wrote the book on Newton. What was his? I can't remember his name. And I think there are history of science courses that you can take, and there is a specialty, but I think it's a pretty narrow field. It's not something I think that the average person graduating in physics or electrical engineering or particularly technical science discipline is exposed to. They're basically required to learn a lot of details about how to do calculations.
Yeah, it depends what course you're doing
as to what they teach you.
And even in these classes, they don't even teach you much about how experiments are performed. You open up a typical physics textbook and it doesn't even say anything about experiments. It doesn't, it'll allude to an experiment, but it doesn't give you any details about how the experiment was actually done. They just say, well, this experiment showed this, and then they give you a bunch of equations. They don't relate how the equations that you're supposed to be using related to the experiment that proves the equations. There's no explanation of how this experiment proves these equations are correct. You're just told these equations are correct and this is what you're supposed to use.
Well, that's from the textbook. If you do a physics degree course, you are doing some experiments. See how they're done.
Yeah, they have a physics lab. That's where they assume that you're supposed to pick up all this, the relation between the textbook equations and how to do real physics. You're supposed to figure that out in a physics lab, which is a separate course.
Yeah. I don't know if it's always a separate. Sometimes combined with what you're talking about. If you're dealing with radioactivity, then you deal with a few experiments dealing with radioactivity.
Okay, but anyway, to summarize, I did a lot of work looking into the history of magnetism and electricity. And I started out with electricity, and what I discovered was that magnetism was a much older, more well-developed, and more understood theory prior to electricity. And it goes back to the era of the Greeks, and primarily because that's where we have writing. There's written records, but the written records are pretty fragmentary, and it goes back to Aristotle and Thales. I don't know if you know who Thales is, but anyway.
Another flop.
It gets kind of fragmented when you want to talk about what Democritus said or what Leucippus said, because the records apparently aren't complete. And so it's pretty clear that Aristotle didn't like the ideas of the atomists. And that's kind of an important thing. And when he talks about the atomists, Democritus and Leucippus, he doesn't really talk about them in a very positive way. So it's kind of clear that atomism wasn't favored by Aristotle. But then later, in the Roman era, Lucretius sort of revised the atomism idea and his work on the nature of the universe, and he tried to rehabilitate the atomism idea, which had been brought forward by I can't remember I can't remember the name of him, but anyway. Yeah. So the Romans were exposed to the atomism idea through Lucretius. Now, the atomism idea fell into disfavor. St. Augustine, I was trying to refer to that before. St. Augustine wrote about how could the magnetic force act. So they had this demonstration where a magician would come in with a silver plate, and he'd have a magnet underneath the silver plate, and then you'd put like nails, iron objects on the surface of the plate. Yeah. And he would move the magnet around underneath the silver plate, and the objects on top would move around following the magnet. Okay. Yeah. And so St. Augustine in his book says, how is this possible? If particles are flowing from the magnet, how do they get through the silver plate to cause the iron particles to move around in response to the motion of the magnet? And so that was a real problem with atomism. And so atomism kind of fell in disfavor because it couldn't explain how the particles got through the silver plate. And I think this is still a problem. Huh?
When particles go through objects, it's mostly empty space.
Well, that's the modern kind of way of viewing it. We say, well, we'll view the silver plate as being mostly empty space, and the atoms are the mass of them is this small thing in the center, and most of the atoms are empty space, and so we can have the photons can fly through the silver plate. That's their current explanation. But I'm just saying that the particle theories couldn't explain that phenomenon. They couldn't explain how magnetism worked with a barrier, okay, of the silver plate between the magnet and the iron particles that moved around on top of the plate. You couldn't explain how particles flowing from the magnet caused that to happen because the silver plate was a barrier. So that was one of the reasons why atomism went into decline during that period.
Yeah.
Okay.
Yeah.
Then later in the Middle Ages, okay, during the Renaissance, there was a renewed interest in Lucretius, the Roman guy. Okay, so there was an interest in Lucretius' theories, on the nature of the universe. His ideas were based on atomism, and it's the Epicureans. Are you familiar with the Epicureans? The Epicureans had advocated this atomism theory, which Lucretius adopted, and so that was what I was trying to explain. Yeah. So there were these Epicurean philosophers who maintained the atomism theory after Aristotle objected to it and pretty much dismissed it, and so it fell out of favor. But the Epicureans sort of maintained this idea, and then that passed on to Lucretius in the Roman era. And then Lucretius was picked up later in the Renaissance. And the other guy that you didn't mention who was really important in this is Galileo. Galileo got in trouble with the Roman Church because he adopted this atomism idea, and that was out of favor at this time. And so Galileo didn't really get in trouble because of his business about the earth revolving around the sun. That was problematic. But he also got in trouble because he advocated atomism theory. And that was another issue that he got in trouble with. And now you have to... Huh?
On the Galileo thing, I think there's part in the Bible which gets interpreted as the earth is moving. And so that's what he conflict with Scripture.
Well, this is a complicated issue, but I don't really want to go into, the way the books tell you about Galileo is it's not really accurate. Okay. It's more complicated controversy.
With the trial for Galileo, it wasn't made public what happened.
Well, that's another issue. The point I'm making is that the Lucretian idea, the atomism idea that was in Lucretius, okay, on the nature of the universe, that got picked up by in the Renaissance period, And Galileo was influenced by that because there was a renewed interest in atomism during the Renaissance, and Galileo sort of reflects that. And so Galileo is also important in the atomism story because he adopted some of the ideas of that. And then that gets later picked up by Newton, and Newton couldn't make he tried to have this corpuscular theory of light, and that didn't really work out. So that you could have said that was an atomism concept, and that didn't really work out. Of course, that got rejected when the wave. What's his name? I forget the guy that when they discovered the wave interference waves of light, they couldn't explain the wave interference experiments using the Newton corpuscular theory of light, and that's when the ether theory comes along. So this whole idea of atomism, particles, and the wave idea, or what we call the field idea. The problem is that throughout history, people have said, well, it's the fundamental thing that causes actions in the universe are these particles, these little atom things. But the issue was that people could come up with experiments that showed that didn't work. So, there were experiments, and this goes back to the Roman era. Okay, today they say that the people and the Greeks and those people, they never did experiments. No, that's not true. That's a big thing. What they would argue is they'd say, I have a theory, and then another guy would come along and say, yeah, but how do you explain this? They didn't call it an experiment. They just said, you can't explain this phenomenon. Okay, and I just presented an example of that, which was the St. Augustine describes the silver plate experiment. Okay, they didn't call it an experiment, but it's an example. So, I mean, it was something that was done. I mean, the guy could come in with a magnet and a silver plate and show that the magnet caused iron objects on the top of the plate to move around, although nothing could penetrate the plate. Okay, and so they said, well, particles can't cause that to happen because they can't get through the plate. Okay, so the theory was disproved by experiment.
It was an interpretation of the same the plate when it's no thought that space and they get through. So you're talking about interpretation.
Well, I mean, it's pretty obvious to them that if there was a particle of magnetism, the idea was that there were particles of magnetism. How did the particles of magnetism get through the silver plate? Okay, they couldn't explain that. People today don't view that as an experiment, but the ancients viewed that as an argument based on a demonstration, which we would call an experiment.
Yeah.
So they did have experiments in the ancient world. Okay, that's but they didn't call them experiments, and they didn't argue in the modern way that we view experiments and how experiments prove things. They didn't use that as a technique. So anyway, so the point is
of experiment. So they were prepared to accept consequences of atomic theory as how it would explain what was going through the silver plate. Basically what they were coming up with.
Well, over the period of time, eventually they decided that in the 19th century, when the idea of the field came along. Mm-hmm. Okay. Mm-hmm. Now at around 1600, Gilbert published this book on the magnet. Okay. And in that book on the magnet, the reason this is important is because he talks about electricity. prior to about 1600, there wasn't really a lot of knowledge about electric effects. Okay, there wasn't really an understanding. They knew, that amber attracted. That if you rubbed amber, it became attractive. It generated an attractive force. But Gilbert, and the reason Gilbert's book is important is because Gilbert basically brought this issue into focus by talking about magnetism and electricity in the same book. And so he tended to sort of unify electricity and magnetism. So you can trace the idea of electricity and magnetism being unified to Gilbert. And the reason is because Gilbert thought that magnetism and electricity acted in the same way. They were both, there was no particle interaction between them. You couldn't say that, a stream of particles or something, a magnet emitted particles or an amber emitted particles, because they could do experiments where they could put objects like a piece of paper in between or a silver plate in between, and it didn't stop the interaction of magnetism. And so the point is that that's where the field theory starts to come into play, the idea of a field. And then Kepler tried to explain gravity on the basis of magnetism, because magnetism acted at a distance without any, it's like action at a distance. One magnet could affect another magnet, and he had the idea that the sun was a giant magnet and that the planets also were magnetic, and that what caused the planets to move in orbits around the sun was the magnetic force between the sun and the planets. That was Kepler's idea. Now, as I mentioned before, when Newton came along, Newton found that he couldn't really explain a magnetic force using the inverse square law, because a magnet is has a dipole field. And the dipole field meant that you couldn't have an inverse square law for the force of magnetism. If the sun was a magnet, it just didn't really work out. And so Newton came up with this force of gravity idea as an inverse square force. But it was similar to magnetism in the sense that it was an attractive force that you couldn't explain how the interaction happened, because it was action at a distance. So there's a similarity between gravity and magnetism, and of course electricity, because electricity is similar to magnetism. Okay, so that's kind of how it works. That's kind of how the flow goes. Okay, and then Boscovich comes on later with with his idea about points being the centers of forces. And his idea is kind of interesting in that it does allow you to explain atoms and how atoms work. But in a very crude way. All right. So anyway, I've sort of filled in some of the gaps. I'm not sure that you appreciate all that or not.
I said it was brief. If you could have talked a lot more about things in the talk. Okay. It was sort of like introduction where this idea of automatism came from, and how it was developed.
Well, it's basically, as you pointed out, yes, you can trace it back. As far as I can see, the historical record becomes pretty murky once you get past the Greek period. If you go to Egypt, it gets pretty murky. I don't think there's any real good documented evidence of who said what. The only documented evidence that really looks to be for sure real is Democritus, and I'm not really sure, and Leucippus, and I'm not really sure that they're, I don't know enough a lot, but I do know that they're referred to by Aristotle. Okay, so I think what we know about that comes from Aristotle when he talks about what they claimed. So Aristotle talks about Leucippus and Democritus, and I think that's where our main knowledge comes from regarding atomism of the Greeks.
Yeah.
People though,
you talk about vague when you get to ancient Egypt, about 20,000 years. But with the Greeks, it's vague as well. People argue some of these Greek philosophers, like Pythagoras, that becomes vague, and he never existed. Euclid, people argue he never did either. So it all gets a bit vague.
Well, I spent a lot of time when I was doing the history of magnetism. This is documented at the General Science Journal. I wrote a lot of chapters. I have them as chapters of a book on history of magnetism. So it's a history of magnetism. I spent a lot of time in the Greek, looking at what is the literature of the Greeks and where a lot of what comes from. And most of it is fragmentary. Okay. It's like Aristotle says that Thales said. Okay. Aristotle said that Thales said this. Okay. Aristotle said that somebody else said something. Okay. Because the written record is that we have is what Aristotle said about somebody else. Okay. So how do you know? How do you know where Thales got his knowledge from? And okay, so they say that Thales got his knowledge from Egypt. Okay. Mm-hmm. And so but the documentation of how the Greeks like Thales and Axiomander and these, I can't remember the other guy's name right off the top of my head. But anyway, these guys had these ideas, you know, and Aristotle mentions these guys and says, so-and-so said this and so-and-so said that. And what those guys said is not really well documented. It's fragmentary. It's just because Aristotle or some other author whose book that we have access to said something about that. And going beyond that to ancient Egypt is kind of speculative, I think. And it's not really... Well, the documentation isn't really there.
About that 500 BC started exploring places like Egypt. Pythagoras was supposed to be introduced to ancient Egyptian knowledge things.
Right, but they don't really know for sure. They don't really know for sure. That's just, you know, there's no documentation that said, there's no letter or written evidence from Egypt that says this is what the Egyptians said that you could relate to what the Greeks said. And so documentation wise, about as far back as you can go is the Greeks. And the earliest,
you kind of like you got the Old Testament stories about Moses, and if you try to look for the Egyptians say about that, it's all very fragmentary.
There's really no documented evidence. So
they dispute that some fragment that they find written somewhere to what Moses was about. And other things like that. But
well, one of the things that you'll find out is, and to me this was kind of astonishing. Like if you listen to a PBS show or something like that, they'll say some ancient Greek believes such and such.
Yeah,
you know, and this guy was the inventor of this idea, and then once you actually track it down and you find out it's like a fragment of like one or two sentences, you know, and so they're telling you that such and such guy believes such and such based on maybe a sentence or two in a fragment that was quoted by somebody later in the record. It's hardly, I mean, to me, it's kind of credible to say so-and-so believes something because of a sentence, one sentence long. And it's all very fragmented. And so these guys speculate, they try to piece together, what these people believe based on very slim evidence. Okay.
That's all they got. They got slim evidence.
Okay, so the point is, what I really wanted to say here is the evidence for what happened back before the Greeks is kind of like not really very reliable. There's some we do know that Leucippus and Democritus, we know there's records about them, and so the modern theory says that what we believe in modern science can be traced back to Democritus and Leucippus because of atomism. They made statements about atoms, and very fragmentary, not very well complete. Aristotle didn't like that, and so he kind of poo-pooed that. But Aristotle wasn't a totalitarian authority. Okay, in the ancient Greek world, there was all these different people saying different things. You had Aristotle's school, you had the Stoic school, and you had the Epicurean schools. You had all these different schools and teachings, and so it wasn't this uniform thing. But we know a lot about Aristotle because his books were preserved. Okay, that's the reason Aristotle is important, and a lot is talked about Aristotle.
It's supposed to be the greatest Greek philosopher.
Well, mainly because his books are preserved.
Yeah.
Okay. Yeah. And we don't know a lot about other Greek philosophers from this period. We know a lot about what Aristotle said because Aristotle was preserved because he was associated with Alexander the Great, and because he was a teacher of Alexander the Great, Alexander conquered all this territory. Aristotle's books got preserved in the different areas in Aristotle's territory. So in other words, Aristotle's books got translated into these other languages where Alexander the Great had conquered. And so his works were preserved better than some of the other philosophers. That makes sense?
Note here. There was burning of the library of Alexandria. And that was
right, and that meant, and it's kind of, basically it's all fragmentary. What we really know isn't very complete, and it's very fragmentary. So the bottom line is that the atomism idea that we get from Democritus and Leucippus, that kind of evolves through as I understand it, the Epicurean philosophers, and gets picked up by Lucretius, who writes the book, and he's a Roman, and he writes a book on the nature of the universe. Okay, and that book didn't really get promoted during the following period. You have the Roman Empire period, and then you have the Middle Ages in Western Europe. And his book on the nature of the universe got rediscovered in the Renaissance. Okay. Mm-hmm. His book was rediscovered in the Renaissance. It survived, but people didn't pay much attention to it. And so what happens, one of the points of the Renaissance, the rebirth of learning, is not so much what they did was they went back and started studying all these ancient books. And there was a fad of doing that. So during the Renaissance, people started reading Lucretius' book, okay, that was written in Latin. And of course, they made copies of it, and everybody started reading Lucretius' book. And that's kind of why atomism gets revitalized during this period of time, and then Galileo gets into the picture. And so does that make sense to you? So what happens with that? What happens with atomism is it's like a fad. It kind of goes out of favor and then comes back into favor, and goes out of favor and comes back into favor.
Yeah. But modern physics is based on the sort of idea of and it's developed it into atomic physics.
Yes, that's because of Galileo.
Yeah.
Modern physics worships Galileo. Okay, that's just, it's like they worship Einstein, they worship Galileo. So anything that Galileo said is the absolute truth.
No.
Okay, now,
Galileo had problems with prize.
Anyway, it's, the whole business with the church, controversy over the church, it's complicated. Because a lot of the things that Galileo said were completely wrong and ridiculous. His claims about comets, ridiculous, wrong. His claims about the tides, ridiculous and wrong. And that got him into controversy with other experts who said, no, particularly the business with the comets. These guys said, this guy at Galileo doesn't know what he's talking about. He's claiming comets, are in the Earth's atmosphere. And they said, no, we did these calculations that show comets are not in the Earth's atmosphere. So Galileo was a controversial figure, largely because a lot of what he said was wrong. Okay. But the textbooks and the history of science books don't tell you that. They make it seem like everything Galileo said was correct. Okay. And that's not the case. So a lot of his controversy with the church was because a lot of what he was saying was wrong, and he created a lot of controversy with other experts who disagreed with Galileo. And that's part of, and that gets simplified to the part of, the Galileo was right and the church was wrong. That's oversimplified.
The church was concerned with its religious point of view, and it didn't want Galileo teachings in conflict with its religion.
Well, a lot of it, as I explained, his theory of the comets was completely bogus. So,
I don't think that development about religion was it. So.
The modern science, the modern books on Galileo try to simplify it and make it into a controversy of Galileo was right and the church was wrong. But it's more complicated than that, and because he stepped on a lot of toes. He had this idea of, he adopted the atomism theory, okay, and that stepped on a lot of toes of people, and so that he pretty much angered a lot of people, okay, and he had a lot of enemies, and so the whole controversy. The whole controversy involves more than just the Earth is the center of the universe controversy. There's more to it than that.
Galileo liked talking with people, and Socrates liked arguing with people. So with Socrates, they said, right, drink this voice. Like him arguing. Galileo arguing. The church told him to shut up.
Well, what I'm trying to get to is that at the time of the Renaissance, what was popular was going back and reading ancient books and rediscovering the knowledge of the ancients. And one of the books was Lucretius on the Nature of the Universe, which was an atomism. It was a theory of atomism, and that's how atomism came back into favor. And Galileo, who essentially tried to advance an atomism theory, and that's where the modern science picks up the atomism as a core belief. So you can trace back the modern science idea of atomism to Galileo. And so they picked it up from Galileo, who picked it up from Lucretius. Does that make sense?
Yeah, well, they don't really teach that to students, but you don't pick up from Galileo ideas to say how they.
Well, I'm sure it's more complicated, but that's the general drift of what happens.
Yeah.
And then later,
it's a long history.
Well, you had, of course, Leibniz in his monad theory. Okay, and and this, Galileo was at the around 1600, so he was at the beginning of the 17th century, and then later you get Leibniz and Newton towards the end of the 17th century. Okay, and then that gets picked up going through the 18th century, and with Dalton, Dalton's idea, and they seem disconnected. Okay, and maybe a lot of it is disconnected, but the atomism idea kind of originates with the birth of modern science around 1600 with Galileo primarily. That's why he's a big figure in the books.
Yeah. Okay.
I'm not sure that
they don't teach it. They don't teach it. They don't teach it to physics students.
Yeah, I didn't. Boscovic, of course, is 18th century, and so he's after Newton in the 18th century. So Boscovic is sort of so it kind of goes like Galileo, then you got Newton. We're talking oversimplification here. Then Boscovic, and then later you get to quantum mechanics in the 20th century.
Yeah.
All right.
So they don't say how give a proper explanation of where quantum mechanics came from, classical physics beginning, and the same thing with relativity. Give it beginnings from earlier theory. Okay. Thank you. So I close now. Because I got to go to the toilet. I'll close the session. Thank you.
Have a good day.
And you. Thank you. Cheers. Good luck. Okay. Bye.